G'day team, welcome back to another quick video on the optimization of situations, but we're going to start applying differentiation and calculus to help us with this scenario. So I've here written a few steps that will help us sort of get through some of our problems. So step one, draw a nice clear diagram of what's going on. Make a formula with the object to be optimized as the subject. So an area, a volume, anything like that. Any restrictions must also be noted. Number three, find the first derivative and the values where the derivative is zero. Okay. We're going to create a sign diagram, which we've done lots of, and we're going to find the maximum or minimum and do that classification. We're going to find the optimal solution, so whether it's asking to maximize or minimize. And we're going to write the answer in a sentence. Okay, so some pretty clear steps there. Obviously, applying them to different contexts can be a bit tricky, but we're going to go through an example together right now. So a rectangular dish is made by cutting out squares from the corners of a 25 centimeter by 40 centimeter tin plate. What size squares must be cut to maximize the volume? So step one, let's draw a diagram. So I've got a nice big rectangle plate that looks like this. Now I know this whole length here is 25 centimeters, and that's the same as down here. And then these two lengths are the same, and that's 40 centimeters. Now I've got square cuts out of the corners. So I'm just going to make my pen dotted. So it's super easy to see that these are my cutouts. So I'm going to just put them into my four corners, just like this. And we've said that they're squares. So that means they are all the same length, and I might just denote that in with a pink single line. Okay, so different to the black single line. Now, we want to maximize volume. Okay. One thing we probably need to do first, though, is assign a value to these cutouts. So let's call them X centimeters. Okay. Now, because we want to maximize volume, we need to create an equation that represents volume. So V with respect to X. Now, volume is length times width times height. The length of my object is 40, but it's minus 2x because I've taken off 1x here and 1x here from my lengths. My width is 25 minus 2x, because same thing, I've taken off 2x's from here, and then my height is just x. Okay, so what I want to do is actually I want to multiply all of this through, and I might move my diagram across a little bit just to give me a bit of breathing room. So I want to expand this out because I want to take the derivative of this. I want it in just single term form that I can apply the power rule to. So we're going to expand this out. So we're going to FOIL it. So I've got 40 times 25, which is 1,000. That is 10,000, 1,000. I've got 40 times negative 2x, which is negative 80x, minus 50x, plus 4x squared, and all of that is times by x. So that means overall I have 1000x, this is negative 130x squared now, plus 4x cubed. Now that is my volume equation, and I might just rewrite this in ascending order. So 4x cubed minus 130x squared plus 1000x. So that is my volume equation for a general x. So that is step 2 done. Step 3, find the first derivative and the values where the derivative is 0. So we want to find v prime of x, sorry. So 12x squared, take 260x plus 1000. Now we want to find those stationary points. So we want to find v dash of x equals 0. So 12x squared, take 260x plus 1000 equals 0. Now, factorizing that by hand is going to be a little bit tricky. So you're more than welcome to use a graphics calculator to help you solve this. I'm going to do that super quickly now. So my x values are going to be 50 over 3 and 5. So we need to work out if any of these do not actually allow us to work. Now 50 over 3 is approximately 12 and 2/3. Okay. 16 and 2/3, sorry. Misread my calculator. 16 and 2/3. Now, if I use 5, I can put 5 in for x here, and I've got just 15, a length here, and then I've got a length of 30 here. If I put 2 times 16 in, so 16 and 2/3 and 16 and 2/3, I've got like 32, 33 almost, and that's going to give me a negative length. So we reject 50 over 3 as a solution because we can't feasibly do it. So my sign diagram now is just 5. So let's choose 0 to put in, and let's choose 6. Now if I put 0 into here, I get positive 1,000, so that's positive. And we are probably going to get a negative, but if I put 6 in, I definitely get a negative because 6 times 260 is pretty big, so negative. That means I've got a maximum at x equals 5. So, therefore, maximum at x equals 5 centimeters. And we want to find the dimensions of that tin plate. So, let's substitute x equals 5 back into here. So we want to find what size squares must be cut. So 5 centimeters. Let's actually find the volume that it maximizes. So v of x, so v of 5. The easiest one to substitute into is this one here. So we've got 4 times 5 cubed minus 130 times 5 squared plus 1,000 times by 5. So that is equal to 4 times 125 minus 130 times 25 plus 5,000, 2,250 centimeters cubed. And that's it. So it's really important that we're looking at rejecting certain solutions and having a little bit of a look at limitations and reasonability in our solutions. Hopefully that helps, and we'll see you guys in the next video.